Okay, in this video lesson, we're going to derive a pretty famous equation in projectile motion. It's called the range equation. And the reason it's famous is because it's one equation that allows you to calculate the range of a projectile in one simple step. In other words, you don't have to go and solve for the time separately before you go and calculate the range. So it's a nice formula for that reason, and it's kind of like a one-stop shopping sort of a formula. So let's make a sketch here of our projectile and the path that it's going to follow. So we'll have the standard kind of ball starting at the off the ground level. The ball is going to be launched with some initial velocity, and of course it's going to follow a path or a trajectory which is arced. So you've got the initial position here and a final position which is at the same height. Okay, so the assumption here is the ball is coming back to that same height that it was launched at. And of course we know at this point that this initial velocity vector, you can box it in. And that will give you the components Vx initial and Vy initial. Those are the two components in the different directions. And we're going to need those components when we set up our equations. Okay, so I'm going to kind of divide my page here into vertical, meaning the vertical direction, and horizontal. And again, my goal is to come up with one equation that allows me to determine the range. And I hope you can see that range is a horizontal quantity. So I'm really trying to get my delta x. That's going to be equal to the x component of the velocity times the time. So in the past, what we would always do is we would then, we would have to, before you can get this range, you'd have to go back and get the time and solve for it. And what we're going to do here is just solve for the time symbolically. We're going to have to go back here to solve for the time, and then we're going to substitute that result into the range formula, and we will get a new formula that doesn't have time. So we're eliminating t. So let's go into the vertical direction. In this particular case, since the particle is going up and coming back down, we know that its displacement is going to be 0. So I'm going to write delta y is equal to Vy initial times t minus 1/2 gt squared. And that's a great equation to use because I hope you can see that going from this initial position to this final position, that is really a vertical displacement of 0 because it's coming back to where it started. I'm also going to point out that I'm taking the negative sign out of g when I write the formula. So when I substitute g in, it will come in as a positive number. So let's write this out. We have Vy initial. That's going to be equal to V initial times the sine of theta. There's our theta. That's multiplied by t minus 1/2 g times t squared. I'm then going to isolate t. By moving one of those terms over and multiplying both sides by negative. And then I'm going to divide out the 1/2 g. And also I'm canceling out a time here. Oops. And so put that in parentheses. So that's what we have as our expression for t. It's 2 times the initial velocity divided by gravity times the sine of theta, our launch angle. All right, so I'm going to take that and I'm going to plug it in up here. My Vx is really my Vx initial, isn't it? Because that never changes. So this becomes V initial cos theta for that. And then for t, I'm going to plug in my 2 V initial over g times sine theta. Okay, then I'm going to group terms. And I'm going to have V initial squared over g times 2 sine theta cos theta. And you might be wondering, why did I put the 2 there? Why didn't I just put the 2 out front like we normally do in physics? And the reason is you may recognize that there's a trig identity going on here. All of this is really just equal to the sine of 2 theta. And so that leaves me with an expression for the range, which is that range is equal to initial velocity squared divided by gravity times the sine of 2 theta, or twice the launch angle. And this is the range equation. Yippee! All right, and you can see that the one thing that's not in here is t, time, and that really makes this equation valuable, because now you can, if you know the launch angle and you know the initial velocity, you can instantly calculate the range in one step, which is awesome. Okay, so that's a good equation to know. Now, just a couple things about it. It also it makes some nice points for us. One of the interesting things here is you can show 2 of the results that we've talked about so far in class. For example, we know that 45 degrees gives the biggest range. That's something we've seen before. And it's pretty easy to show why now, because you can approach this from a calculus point of view, and you can say, well, what if I take my function for the range and I basically take the derivative of that function for the range. I know we called it delta x before, but I'm going to call it x now. So if you took the derivative of the range function and you set it equal to 0, okay, that's going to be allowing us to find a critical point. Okay, so this is a critical point. So where does that range function actually kind of have a point where its derivative doesn't change? And what that's going to mean is it's going to be a kind of a maximum. And at that point, that should be the angle theta that gives us the largest possible range. So let's see what that would look like. That would mean taking the derivative of v initial squared over g times the sine of 2 theta. Okay, so that's my range function. I'm taking the derivative with respect to theta here. We've never done this before, but it's really the same as taking the derivative with respect to any variable. And what happens is that the vi squared over g is a constant that just comes out because it doesn't depend on theta. When you take the derivative of the sine of 2 theta, the 2 is going to pop out, okay, because the 2 is part of the argument, and the derivative of the sine is the cosine, and the argument never changes when you take the derivative in that sort of a way. So the derivative of the sine of 2 theta comes out to be 2 times the cosine of 2 theta. And so this whole expression then becomes looking like that. So the question would be, when is that equal to 0? Okay, so when does that happen? And of course this front part doesn't matter because that's never 0. So the question is really, when is the cosine of 2 theta equal to 0? And that's going to happen at theta is equal to 45 degrees. And I hope you can see why, because 2 times 45 degrees is 90. The cosine of 90 is 0. So basically what we've just shown is that 45 degrees is kind of like your critical point, and for that reason, you're going to have the largest range possible, when you're at a 45-degree angle. Okay. By the way, if you want to prove it to yourself that that's actually a maximum, not a minimum, because we kind of assumed it was a maximum, you could take the second derivative and check to see that it's positive at 45 degrees. That's the concavity test that they teach in calculus. But I'm not going to do that here. The other thing that we'll say about the range equation that's nice to know is we talked about complementary angles give the same range. A little bit of shorthand there. Complementary angles give the same range. And that's pretty easy to see because if you think about it, again, the range equation is going to be your delta x is equal to v initial squared over g times the sine of 2 theta. But what I'm going to point out is that a trig identity, which says that the sine of theta, of any theta, is equal to the sine of 180 minus theta. That's something you learn in math class. And if that's true, then the sine of 2 theta should be equal to the sine of 180 minus 2 theta. Okay, and so that is saying that it's kind of like saying that the sine, if you call this is a little bit awkward, a little bit slightly awkward case to make, but if this is going to be the angle you're talking about, 2 theta, then half of that would be 90 minus that angle. Okay. I don't know, that's kind of awkward to say it that way, but the point is that if you plug in an angle here for sine 2 theta and calculate the range, plugging in 90 minus that angle back into that expression is going to give you the exact same range. So that's the kind of the point to make here is that if you make this your angle, then 90 minus the angle is going to end up being equal to the same thing. If you want, try it on your calculator. Make up an angle, make up a theta value or whatever, and try it out. But it does show that you get the same range for complementary angles. Okay. So this is a good equation to know, the range equation, and it does pull out some other physics that it confirms some stuff that we've talked about. Okay, so that's about it. Have fun.